starting soon. All right, let's get this bread. So where I stopped yesterday is halfway. Sorry, just a second. Okay. Okay, let's do this now. Let's get this bread. So, where I stopped was at the following. What my plan was is to understand how this works. The fast inverse square root algorithm. So what I want here actually is to read this and hopefully understand it and hopefully know what the thing is all about. In the last episode, I had some hiccups with understanding the float representation in the IEEE 754 standard. I think I get it. So now I think I can skip. Actually, I don't need to skip. I want to read this. Reread. 32-bit floats representation. Yeah, so this is the IEEE 754 standard. And in this standard, the float has three members. It has the mantissa, the exponent, and the sign. Okay, sign indicates whether the number is positive or negative. This is the range of the number, and the mantissa is linearly specifies where exactly in the range this number lives. The following equation shows how the actual numerical value n is conceptually derived from the three integer parts. Okay, so this is the sign, this is the exponent, n is the mantissa. If we break all of this into the mantissa, we set this constant to 127. E is this, we get this formula. The little trick to get the sign bit from a 0 or a 1 into a -1 or 1. Instead of simply multiplying by m, we multiply by 1 plus m. This ensures that when m is 0 and when m is 1, we get 2e plus 1, the full range. So when m is 0, so this is 0, we get 2e, and when m is 1, we get 2e plus 1. Okay. So this is how an example number like this would look like with this representation. All right, let me just go back. Let me do another refresher. Wait, just a second. Let me do another one. Let me do another one, just a second. 260. I'm just gonna paste this here. Wait, not this one. I watched this the last time. Wait. This was the link.
Howdy, my name is Sabashalini and I'm here to explain how to represent a number in IEEE 754 32-bit floating point notation. I'm going to consider the following number for an example, 263.3.
Alright.
Now the first step that goes into this is to convert the following number into its binary form. We know how to convert 263 to binary form. It's very simple and we have learned that before. You just keep dividing it by 2 and keep track of the remainder. So in this case, it'll be 131. The remainder is 1 divided by 2 again. It's 65.
I like the format of the author.
Divided by 2, you get 32. Remainder is 1. You get 16. Remainder is 0. This is the last step where you get a 0 in this column, and this is where it stops. So 263 in binary form are just the remainder bits in this order.
Alright.
So 263 in binary form is 1, 0, 0, 0, 0, 0, 1, 1, 1. Now we have to convert 0.3 to binary representation, and this entails a different procedure. So in this case, you start multiplying by 2 to the digit after the decimal point. So 0.3, you multiply by 2, you get 0.6. Now, you have to keep track of the digit that precedes the decimal point in this column. So in this case, it's 0. So keep track of the 0. Now, take this over the next step, that's 0.6 times 2, and you get 1.2. Keep track of this digit, that is 1. Instead of doing 1.2 times 2 for the next step, you just take the digit that follows the decimal point along with the decimal point. So that would be 0.2 times 2.
Alright.
And you get 0.4. This digit 0. Then 0.4 times 2, you get 0.8. Keep track of this digit, that's 0. And then 0.8 times 2 gives you 1.6. Keep track of this digit, that's 1. So doing 1.6 times 2, it will be 0.6 times 2, and it will be 1.2.
But now it repeats.
1. Now you can observe that this step is essentially this step. So you know after 0.6, you would again follow with these steps, and then it would loop again. So instead of doing everything in writing, you can just assume it's going to go back to that step. And so this column would be 0, 0, 1, 1, goes back again. So it would be 0, 0, 1, 1, so forth. So 0.3 in binary representation would be 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, so forth.
Okay.
So the first step was for us to represent 263.3 in binary form, and that is 1, 0, 0, 0, 0, 0, 1, 1, 1, point 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, so forth. Now the second step would be to represent the binary form in scientific notation. So in this case, you need to shift the decimal point to the left till it reaches this point. So we will be shifting it 1, 2, 3, 4, 5, 6, 7, 8 times. So for each shift to the left, you need to multiply the number by 2. We're shifting it 8 times to the left. So in this case, we will be multiplying it by 2 8 times, that is 2 to the 8. So in writing, that would be 1.000000011, 0.00110011, so forth, times 2 to the 8th. This is the scientific form. Now the third and final step will be writing this in the IEEE 754 format. So the format suggests that the first bit should be the sign bit. So let me just write it in X's to make it clear. So the first bit will be the sign bit.
Oh.
And protocol says that if the number being considered is a negative number, the sign bit will be assigned as 1. And if it's a positive number, it will be assigned as 0. So since 263.3 is a positive number in this case, our sign bit will be 0. The next 8 bits of the representation are the exponential bits. That is the exponent of 2 in the scientific notation, 8 times to the left. So in this case, we will be multiplying it by 2 8 times, that is 2 to the 8. So in writing, that would be 1.000000011, 111, 01, 0011, 0011, so forth, times 2 to the 8th. This is the scientific form. Now the third and final step would be writing this in the IEEE 754 format. So the format suggests that the first bit should be the sign bit. So let me just write it in X's to make it clear. So the first bit will be the sign bit, and protocol says that if the number being considered is a negative number, the sign bit will be assigned as 1, and if it's a positive number, it will be assigned as 0. So since 263.3 is a positive number in this case, our sign bit will be 0. The next 8 bits of the representation are the exponential bits, that is, the exponent of 2 in the scientific notation. Now we need to take care of the bias because in the 754 representation, the exponents has to cover negative and positive numbers, and so they have given a certain number as the bias value, and the exponent bias for single precision number is 127. So if you have a negative number here, you subtract it from the bias, and since this is a positive number, you add to the bias. So now we need to take care of the bias because in the 754 representation, the exponents has to cover negative and positive numbers, and so they have given a certain number as the bias value, and the exponent bias for single precision number is 127. So if you have a negative number here, you subtract it from the bias, and since this is a positive number, you add to the bias. So our exponent bits in this case would be 127 plus 8, and that is 135. Yep, and this is in decimal form, so when you convert it into binary notation using the steps that I've already shown you how to, you'd get 100001111. And these are the fraction bits. So we will have 23 fraction bits, and that is essentially the bits that follows the decimal point in the scientific notation. This is also known as the mantissa. So the fraction bits in this case would be 000, 00, 111, 01, 0011, 0011, so forth. So the final IEEE representation goes as follows. So it's just combine all these bits together. You'll get the answer. So it's 0100, that's the first 4. Then 0011, that's the next 4. 1000, combine these 4. I'm just separating into 4 to make it more convenient for us to observe. 0011, 1010, 0110, 0110, 0110, because this goes on. So 4, 8, 12, 16. We have 32 bits over here, and this is the final representation of 263.3. I hope this was
Hey everyone, in this video we're going to learn how to convert a decimal number to IEEE 754 single precision format, which means that we're going to take a decimal number like 45.45 that has a decimal point and convert it to a representation that uses 30. Bits, hence the single and single precision. If you are taking compo work in fall of 2015, you may recognize this problem because it's number 2 on homework 5. So let's go and get started. The first thing we're going to do is we have to convert sort of the left-hand side of our decimal point to binary, so that's 45. So let's go and do that. This is pretty standard procedure. You know, you've done this tons of times from, I think it was homework 1. But yeah, let's go and get started. So 45 can be represented as 22. So you get the idea here. I'd really recommend using a pencil. You know, everybody makes mistakes. People always go to me and they say, Steven, you're a TA. You really shouldn't be making any mistakes here, but nobody's perfect. I mean, if you get 100 on your exam, you're basically perfect. Like, you can go and like tell your parents, like, hey mom, hey dad, I'm a perfect student. But I mean, you have to be realistic. Like, you're not gonna get 100 on the exam. Like, if you were gonna get 100 on the exam, you wouldn't have to watch this video. Like, let's be real. Anyway, so we can stop now that we have this quotient at 0. Once this value reaches 0, not this one, this will never reach 0, and not this one, then we can go ahead and have our conversion. So this is pretty standard. We're going to read our remainders from bottom to top. So we can write that down. So this is our representation of 45 in binary.
Okay, I think I said I had a slight microphone mishap. Basically, I'm a brainlet. I can't understand this. So
there's the sort of
this is the whole recap of everything.
Convert the right-hand side. So we're going to go ahead and convert
Okay.
45, not to be confused with 45. Okay, this is a slightly different procedure, but it's nothing too crazy. So I wrote an equal sign, but I'm going to erase it because remember, pencils are important. So what we do is we take our value and we're going to multiply it by 2 a bunch of times, and then take the value that we get and do it on the next line. You'll see what I mean if you follow along. So we'll take 0.45, multiply it by 2, which will give us 0.9. And I really recommend, I'm going to go ahead and make this a column. I'd recommend writing a 0 whenever you encounter one. Don't leave it off because it'll help you read it in a bit. You'll see in a second. So we'll take 0.9, multiply that by 2, which will give us 1.8. And then when we copy 1.8 over here, we're going to go ahead and ignore the fact that this is a 1. So we're going to just ignore this 1 and just copy over the 0.8. Times 2 equals 1.6. And again, with the 1.6, we're going to ignore the 1. Just make it 0.6. And this is going to be 1.2. Copy over just the 0.2. Times 2 equals 0.4. And then we're just going to copy over 0.4. 0.8. Now, I could keep going here, and I would keep getting more and more values for our right-hand side. So like more and more bits after the binary point. But the thing is that this is just going to repeat a cycle starting with this. So if I were to copy the 0.8 over, I would put 0.8 here and multiply it by 2 and get 1.6. But you can see that we have a step that looks just like that right here. So what I'm going to find out is that this whole section of 1100 is just going to keep repeating, because I'll put a 0.8 here, and then it'll be 0.8 times 2 equals 1.6, and then this will equal, like 0.6 times 2 will equal 1.2, and this will just keep on going forever. So we know that our right-hand side is going to be, and you read this from top to bottom because you're multiplying, and it's just kind of like the opposite of doing this. Our right-hand side is going to be 0, 1, 1, and then we know if I write these other, did I get that right? 0, 1, 1, 1, 0, 0. I know that this particular portion is going to go on forever, so I'm going to put a bar above it
Wait. So, okay, I understand these parts. I understand why he does this, and I understand why he does that. Yeah. Hey. Yeah. I am aware of that. I just want to know why it works the way it works. Why is it represented like this? How does the why this works like this?
So keep that in mind, and it ends here. Now what we need to do is we need to take this value and we need to get it into a format that is sort of like scientific notation in decimal, but in binary and in terms of powers of 2. So what we're going to do, if you remember from scientific notation, if we have a value like...
Man, I can't believe I think I'm a literal brainlet. I think that JavaScript fried my brain, like, completely.
You know, 123.4, and we want to express this in scientific notation, we have to move this point to after the first digit. So this will become 1.23. It's kind of like the opposite of doing this. Our right-hand side is going to be 0, 1, 1, and then we know if I write these other, did I get that right? 0, 1, 1, 1, 0, 0. I know that this particular portion is going to go on forever, so I'm going to put a bar above it to make note of that. So let's keep that in mind, and it ends here. Now,
what are the implications of this going forever?
what we need to do is we need to take this value and we need to get it into a format that is sort of like scientific notation in decimal, but in binary and in terms of powers of 2. So what we're going to do, if you remember from scientific notation, if we have a value like 123.4,
okay,
and we want to express this in scientific notation, we have to move this point to after the first digit. So this will become 1.234 times 2. That's pretty easy. Now with binary, when we move the binary point around, we're not multiplying by 10 anymore, we're going to be multiplying by 2.
So that's it. So this is the way we actually represent numbers in the scientific notation. So we'll most probably do the same here. I haven't read the RPSC. So yeah, I mean, basically, why I'm doing this is I want to run through this method. I want to understand the fast inverse square root, but who would have known that one of the most important things of this algorithm, actually not the most, the first hurdle are the floats and the representation of them in the computer. And also there's gonna be a lot of shit like bit shifting. So
So we're going to take this binary point and move it over here after the first one to get this. So we're going to
-1 over n times 0, 1, 1, 1 times 2 over 0, 1, 1.
get 1.01101, and you just copy your whole bit string down. So let me make sure I got that right.
Okay, so now he's gonna multiply it by okay. Now he's gonna multiply it by how many numbers he has here? He has here 0, 1, 1, 0, 1. So there are 5 numbers. So he's gonna multiply the whole new number with 2 over 5, right?
5 places to the left, so that's going to be times 2 to the 5th. So this is a useful representation for us because it gives us our mantissa.
I know that it's not. I know that it's not a smart approximation. I remember the problem I'm having is, I remember reading it the first time, being flabbergasted like by it. It was like another universe, and a couple of days ago I think I saw like a I don't know what even it was, an article, and it was mentioned there, and I open it, and now things are somewhat clearer. I just want to, understand it. I remember 8 years ago I fucking saw it, and I said to myself, yeah, I want to understand how this works. I don't think it's even used at all anymore for what was it, the lighting vectors, stuff like that. Just a moment, I'm gonna be there in a second. Alrighty, minor technical problems. By technical, I mean I have a pretty small water bottle and I need to refill it every time. Okay, so I understand this.
Our IEEE 754 format, it gives us our exponent, and we know that our sign is positive because 45 is a positive number. So let's go ahead and write that down. So we've got our sign is equal to 0, and we have that our exponent is equal to 5. And our mantissa is, oh boy, just copy. There we go. So with these 3 values, we can now sort of insert this into our little, one second, I'm going to go ahead and notate real quick that these repeat. So we're now ready to break this out into its component binary parts. So when we have an IEEE 754 single precision floating point binary number, that was a mouthful, it looks something like this, and go ahead and ignore the lines on my graph paper because this isn't going to be like to scale. So we have a sign bit, and then we have 8 bits of exponent, so I'll just write exp. And then we have a mantissa, which is everything following this 1, so all of these values, which can be represented with 23 bits. Now, one thing that's going to be interesting is that when we go ahead and insert our mantissa into this template, our mantissa goes on forever. It is infinitely precise in binary. Even though in decimal, we can represent 45.45 with exact precision. This value is exactly 45.45. In binary, this is a repeating sequence. So this is kind of cool because we have a number in binary that cannot be represented precisely with a computer that can be easily represented in decimal. So I'm going to go ahead and fill this in now. And there is one special thing to note is that our exponent field has what's called a bias. So I'm going to go ahead and write this here. It is biased. Now we know that with 8 bits of information, the largest integer value that we'll be able to store will be 2 to the 8th minus 1, which is
yeah, that's why
200.
Okay, Okay, now I understand why.
55.
So now I understand why he has the exponent that consists of 8 numbers.
And the thing is that our exponents are often we're going to want them to be negative because that will allow us to represent small numbers. If you have a small number with scientific notation in your exponent, or if you have a negative exponent rather with scientific notation, you know that you're going to be representing a very small number. So
the exponent will be actually 2, it will be, wait. I forgot I have my tablet connected all the time. So let me open this. No. Where are you? You are here. Okay, I want you. And if I open you now, all right. Now I forgot what I want. Yeah. So what the exponent actually is, I assume, will be it will be the range between, yeah, wait. Let me just close this. I think I have it.
Creators of IEEE, or what the people at IEEE decided to do was, instead of using 2's complement or some kind of representation like that, they decided to simply bias the exponent. So in our exponent, if we see the value, like if we inspect the register and we see the actual value, let's say all zeros, then we know that our value is actually going to be negative 127. And this seems arbitrary at first until I do a few more examples. So if we have all 1s, which is the largest unsigned integer that can be stored with 8 bits,
So it's going to be,
instead of being 2 to the 8th minus 1, 255, this is actually going to be 128. So basically, we take the value that's actually stored in the physical register on the computer, and we subtract 127 from it, and that's our actual value. So now when we want to insert 5 as our exponent, 5 is here and there. When we want to insert 5 as our exponent, what we actually want to put in here is 5 plus 127. Because when we go from register to paper...
I get it. Wait.
To scientific notation, we want to subtract 127. But when we go from paper to IEEE, we want to add 127. And the reason they chose 127 is because it's half of this value under integer division. So what we're going to do is we first have to take 5, and we're going to go ahead and say, because 5 isn't equal to 132, but we're going to say that it maps to 132 because of the standard. So we have to represent 132 in binary, which is pretty simple. So we have 128 plus 4. That's easy. So here's the actual value that's going to go into our exponent. And then our sign bit and our mantissa are just going to go in there literally, except our mantissa, we're going to take these repeating bits and copy them as many times as we can to fit. And sometimes what people will do is they'll store, they'll try to round up. And if you go to some online calculators, they'll also do this. But for the purposes of this class, just take repeating bits and copy them as far as you can go. So what we're going to do now is we're going to copy our sign, exponent, and mantissa into our little template. So we're going to have 1 bit, followed by 8 bits, followed by 23 bits. So just go and copy these down. So I'm just going to copy the exponent bits. And then we'll copy our mantissa as far as we can go. And I'm going to count to 23 so that I can get as precise of a number as possible. So I'm going to go ahead and do 0, 1, 1. So we got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And we're done. That's the solution.
Okay, I might not be a brainlet after all. I think I am, but... The thing is, I understand why we do everything, but why has it chosen this logic? Where are you? E754. Geeks for geeks. Like this site. I use it all the time when I studied at college, but I don't think it's very useful now. Let me see this. Let's see what Wikipedia says. Blah blah blah. It's a technical standard for floating point arithmetics, originally established in 1984, but by the Institute of Electric. Okay, I don't. So format is a set of representations of numerical values and symbols. So it's basically just the way we include we encode our set, right? So a floating point format is specified by a base, which is either 2 or binary, 2 or 10, binary or decimal, a precision p, an exponent, floating just a second. Floating point formats. That's not it. Explaining E754 floating point representation. Let's say I have this. In binary, this float is represented as this. All right. What I don't understand is how this representation. The exponent is 0 once you subtract the bias, and the fraction part of the... How does 1 scaled by nothing equals this? Wait. I mean, this is simple. This doesn't tell me anything. Basically, here we just have the general case in which n over minus m is just equal to 1 being divided by n over m. So if we have 10.007, if I have 007, okay, I'm gonna get this some other way, but I want to talk about this. So it's gonna be 0 times 10 minus 1, 0 times 10 minus 2, and 7 times 10 minus 3. So it's gonna be 7 or 1,000, right? And that's 007. Which makes sense. This makes sense from a decimal standpoint. But I don't know why is this important. The binary number 1 is 1 times I'm not just a perfectionist trying to understand this. I mean, I know how we get this. I know how we calculate this. I think I'm just interested in why we use this, but a specific way of converting. But I can't read it anywhere. I can't find it anywhere. So this is 1, this is 4, this is nothing, this is nothing. So this will be, wait. So it's 1/2, 1/4, 1/8, nothing, 1/32. So this is 5. Probably was easy to make hardware for. Yeah, I think I think I think they most probably found the optimal way to represent floating point numbers based on the hardware they had, but I would like to read something that's between a Wikipedia article and these pretty simplistic answers. Something with some background. You want to read this? Is this actually it? Standards. The page you are looking for is either removed or temporarily unavailable. All right. I'm a novice and I'm feeling like a nitwit right now. Yeah, I feel you. I apologize for any ignorant statement or inaccuracies in advance. For the past 2 days, I have been racking my brain against floating point numbers. All right, I don't care. Okay, there's 1 sign bit, 8 exponent bits, and 24 significant bits. The significant is multiplied by the base 2 exponent in order to shift the radix point to the desired location. All right. Okay, we have a base number and an exponent, of course. In hexadecimal, the number 1, 2, 3, A, B, C might be represented as this. In binary, the number this might be represented as this. The sign bit. Oh god. Oh god, I think I got a epiphany. Wait. I think I understand. Basically, okay, the sign bit is not important. I mean, the sign bit is important, but it's not important in this scenario. Basically, the exponent just says how many times we move the radix in the fraction, in the mantissa. I think I get it. I think I oh shit, sorry, I forgot my tablet screen is on. Oh yeah, what are the ranges of these numbers? Let's continue. It takes essentially a 32-bit number and reinterpreting the fields to cover a much broader range. Something has to give, and that something is precision. For example, regular 32-bit integers with all precision centered around 0 can precisely store integers with 32 bits of resolution. Single precision floating point, on the other hand, is unable to match this resolution with 24 bits. Thank you very much. I'm trying to grasp how this standard that represents floating point number works. I understand the logic behind it. If I'm your channel name means sadness in Hindi, so it's like the sadness, truly suited for a channel involving coding. Yeah, we are sad people. Why would you say this? Oh my god. It's 20 minutes to 1 here, and I'm coding. Yeah, it is sad. I'm not even coding. I'm learning something trying that I won't even need. Ah, God. How is this possible? In my language, it translates. Actually, in the old versions of my languages, it means a ghost. It's interesting. Hindu is, I think, part of the Indo-European languages, right? So maybe some words have similar origins. Indo-European similarities. Wait, Hindu is from the belongs to the Indo-European Hindu language. It is. Yeah, it is. So it probably has some similarities. Maybe it originated in the same. Yeah, I think ghosts are usually related to being sad. Wait. I'm learning, people. Wait. Don't bother me. Uh, there are several ways to prevent real numbers on computers. Alright. Fix. I started reading. During its 23 years, it was the most widely used format for floating point computation. So it's not even used any. Okay. So it was the first iteration. Then they changed it in 2008. Okay, represents numbers in binary, providing definitions for 4 levels of precision. We have single precision. Okay, so it can provide a big range of numbers, and the precision is approximately precise to 7 decimal digits. All right. The standard also defines representations for positive and negative infinity and negative 0, blah, 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 blah. This is the single one. See text for explanation. All right. 1 8 plus 1. Wait. Did I mention I hate long doubles? I hate this. BRB, I'm just gonna go for another water refill. Also, I think my brain's gonna work better after I walk. Just a second. Hi, I'm back. So let me just check the comments. I had to check long doubles are 10 bytes on my machine. The match I long double from what I've heard. It's either 120 bits or 80 bits. Yeah, well, I think the only time I had to use a precision like this was in university when we worked those mathematical iterative what was it, like the Newton's series or something like this? No idea. What the fuck was it? I can't remember. No idea. Okay, this is, I assume, simple. They are multiplying it by 2. One more time. I assume the third time the result is something like 1 point something. The next time 0, the next time, the last time is 1. So this is the binary representation of it. Actually, we need extreme precision. I heard that landing on Mars is a matter of like being correct up to I don't know how many hundreds or thousands of decimals. We need this. That's why I'm trying to understand this. I mean, I know how it's no. Okay, let's try this. Sorry. So what do I have? 0.15625 base 10 is what? Multiply by 2. What's this? 0. 0.3125. That's the 0.013125 times 2. Yeah, it's 0.625. 0.625 times 2 is gonna be a 1. So it's 0.57. Oh no, I messed this up. It's 0.25. Dummy. If you haven't watched, you can watch the gradient. Oh, okay. Thank you very much, Dimitri. So let me just put it here. Gradient half decent video late. Yeah, I'm gonna take a look at this. So 0.20, no, it's 0.25 times 2 is 0.5, and 0.5 times 2 is 1. 0.0 I get. Okay, why have I even done this? Single non-zero digit on the left and decimal point. We rewrite this number so it has one single 1 bit to the left of the binary point. So that was all. Fuck, I understand this now. I mean, I understand why and how it works. Yeah, I wrote it here. I'll definitely gonna check it. By the way, since I started using Joplin, I'm much better organized. I also have like a calendar that I try to fill. I always thought that organizing your day and your shit is something attention-seeking people do, but it really helps. It's a really helpful thing. Now we can read all of these functions. Okay, wait, where did I stop? Where did I stop? Here. numbers without a single. Oh, I got a brain freeze. The last 1 minute, I thought about a football match that I just watched. Okay, so this guy is this guy. The only difference is it's rewritten in the scientific notation. All right, and the other difference it uses the base 2 instead of base 10. So the fraction is 0, 1, exponent is -3. So basically, what we'll do when represent this is the same thing, I think. The same thing. Let me see. So assign. Okay. Okay. So why we have this in the bias is because we have 8 bits to represent here. No, this is the double precision. Here we have 8 bits in which we are representing this. And 2 over 8 is 256. And if we divide this including 0, if we divide this into a range, it's going to be from 127, actually 120. What? How can you have both positive and negative 0? Sign 0 is 0 with an associated sign. Arithmetic, the number 0 does not have a sign, so that -0, +0, and 0 are all equivalent. However, in computing, some number representations allow... Okay, we can have 2 zeros. I mean, this might make sense in complex mathematics. All right. Precision is defined as the minimum difference between two successive mantissa representations. Thus, it's a function of only in the mantissa, while the gap is defined as the difference between two successive numbers. Single precision number occupied 32 bits. Floating point. Years ago, I wrote an article about how to do epsilon floating point comparison by using integer comparisons. Alright. The articles have some flaws. Ooh, why? Why is everyone sending me to Wikipedia? What? Why is everyone sending me to Wikipedia? A 32-bit float consists of 1-bit sine field, an 8-bit exponent field, and a 23-bit mantissa field. The union below shows the layout of a 32-bit float. It's a violation of the aliasing rules for some compilers. Ah, it's C++. So this will be the float, this will be the integer, these will be methods, what we have in the struct. Okay. So we have an union. They're all sharing the same memory location, including float and integer value. Okay, so what's this? This is a constructor, right? Yeah, it's a constructor. Okay, so it does what? It's the f. So it assigns this to f, but how does it assign? Most probably these two will now share the same memory, I assume. Thank you very much. Yeah, I think I'm gonna do this. Thank you. I think I'm also gonna call it quits for today. It's already 1:10. I need to go to sleep as well. I think I'm gonna continue this tomorrow. Thank you. Thank you for the comments. They were amazing. I wrote some of them down. I'm also going, so